Hi everyone, and welcome to Chapter 2. I'd like to begin with a quick geometry review. I need you to find the area of the triangle formed by the two red line segments and the x-axis. So the area of, the area underneath this curve, the area of this triangle. Please pause the video for 1 minute and allow students to find the area. Okay, hopefully you remember that the area of a triangle is 1/2 the length of its base times the height perpendicular to the base. So the base of this triangle is 4 units, and the height of this triangle is 0.5 units. And we should have gotten an answer of exactly 1. The area of this triangle is 1. This is going to come back and be important later in the lesson. So Chapter 2 is all about describing location within a distribution. In Chapter 1, you learned how to plot a set of data and to describe its center, shape, and spread. Sometimes, though, the overall pattern of a large number of observations is so regular that we can instead describe it using a smooth curve. So I can take this histogram, and this histogram is based on so many observations, and I see this really clear pattern. And so instead of just using the histogram, I can smooth over it using this curve. You've seen me do this a few times, and this curve is called a density curve. A density curve is an idealized description of the overall pattern of a distribution, and we basically rescale the graph to force the area underneath a density curve to equal 1, meaning 100%. Here 1 means 100%. So we just kind of like shift the y-axis. The y-axis becomes kind of unimportant, and we define the area under this curve to be exactly 1. Density curves come in all of the shapes that you're used to. They can be symmetric, maybe they're approximately normal. They can be skewed, they can be uniform. They don't actually have to be a curve, they could be geometric shapes. The area of a region of a density curve represents the percent of observations that fall in that region. So for example, if I were to find the area, I'm looking at this approximately normal curve, if I were to find the area of this section of curve right here, that would represent what percent of observations fell between this x value and this x value. So let's say the area underneath here is, I don't know, let's say that looks like about 0.22. That means 22% of observations fell between this number and this number. The median of a density curve is the x value which cuts the area in half. So we can see on this skewed right curve, the median is right here, which means the area to the left of it is 0.5 and the area to the right of it is 0.5. And we say the mean of a density curve is its balance point. In this skewed right curve, you could see that the mean is bigger than the median. It's larger than the median, and that's because of that right skewness. So I'm bringing back the triangle from your warm-up. My first question is for you to explain why the figure is an example of a density curve. We already did this in the warm-up. The reason it is a density curve is because the area underneath is exactly equal to 1. What percent of observations fall, for example, between 0 and 2? Well, that would be the area under the curve between an x value of 0 and an x value of 2. That's also a triangle, and so that area is going to be 1/2. The base is 2, and the height is 0.5. And so I get 0.5 or 50% as my answer. And that makes sense. That's half the curve. I'd like you to pause the video and find the percent of observations that fall between 3 and 4, as well as 1 and 3. Okay, for 3 and 4, I'm really hoping you didn't say 25%. I'm really hoping. Because between 3 and 4, this curve is not, uniform. This 3 and 4 does not represent 1/4 of this curve. In fact, that is another triangle. So 1/2, the base is 1, and in this case, the height is 0.25. So 1/2 times 0.25 is actually 0.125. or 12.5%. By the way, you can leave your answer as a decimal or you can write it as a percent. It doesn't matter. And in fact, I really kind of prefer the decimal, and you'll see why much, much later in the class. Finally, what percent of observations fall between 1 and 3? I've kind of marked this up too much. Let me see if I can change the pen color. So between 1 and 3, that's all this in the middle. There are a few ways you can approach this. I'll show you 2 of them. The first that I would probably look at is maybe cutting this into a square, hope you can see that, and a triangle, and adding those 2 areas together. And so the area of that square is going to be base, which is 2, times height, which is 0.25, plus the area of that upper triangle is going to be 1/2. The base is 2, and the height is 0.25, the distance between 0.25 and 0.5. And so 2 times 0.25 gives me 50%, plus 1/2 times 2 times 0.25 gives me 0.25, and that's 0.75 or 75%. You could have also realized that since this small triangle, as we found in the second question, had an area of 0.125, this one, which is symmetric to that one, is also 0.125. And if you add those together and subtract from 1, since that's the total, you would end up with 75%. I'm okay with either of those. I want to talk about an extremely important example of a density curve, and that's the normal distribution. All right, we talked a little bit about approximately normal shapes in chapter 1. And so I want to give you a lot more information about the normal distribution here. We know that it's symmetric. We know that it's bell-shaped. It has a single peak in the center. It looks something like that. And remember, you're not allowed to call something normal. You have to call it approximately normal, because normal means something really mathematically specific that I'm going to get into right now. The shape of a normal distribution is determined 100% by 2 parameters, the mean and the standard deviation. In other words, if I know the mean and standard deviation of a normal curve, I have everything I need to find out everything about that curve. I want to pause here and talk about notation. You're going to see 2 symbols that you haven't seen yet in this class. These are Greek letters. This is the Greek letter mu, and this is the Greek letter sigma. The Greek letter mu is used for mean, and the Greek letter sigma is used for standard deviation. And I know you're wondering, hang on a second, Miss Kramer, yesterday or last week or whatever, you said that X bar was mean and S was standard deviation. And I was not lying to you. There are times when we should use X bar for the mean, and there are times that we should use mu for the mean. And likewise, there are times that we should use S for standard deviation, and there are times that we should use sigma for standard deviation. Right now, I want you to be comfortable with both representations. So regardless of if I tell you X bar or mu, I want you to understand that that's the mean. And regardless of if I give you S or sigma, I want you to understand that that's standard deviation. We'll talk more later in the year about when it's appropriate to use one versus the other. There is an answer to that. But right now, I just want you comfortable with this new notation. So practice on your paper, making some mu's and making some sigmas. The mu is just a U with a little tail to start it, okay? It's the Greek letter M. And then the sigma is just like an O with a little kind of hat on top or something like that. It's not an R. I know sometimes when I start drawing them quickly, they may start to look like R's. I get frustrated when students say, hey, Ms. Kramer, what's that little R thing you keep drawing? When we've been talking about sigma since the 3rd week of school. So this is sigma. It's an O with a little line coming off the top of it, and it's meant for standard deviation. So I want you to show you this abbreviated notation. Capital N 5, 2, like that, means that a distribution is normal with a mean of 5 and a standard deviation of 2. Again, since the normal curve is a density curve, the area under it is exactly equal to 1. All 3 of these are approximately normal density curves. They all have a mean of 0 because the mean is located exactly on that peak, and you can see on the x-axis that's 0. The red one has a standard deviation of, this says 1.5, and I see that it's more spread out. I have a greater average distance to the mean. The black one in the middle has a standard deviation of 1, so a little smaller, a little more compact. More observations are closer to the mean. And then the blue has a standard deviation of 0.7. That's the smallest of the 3. It's the most crunched towards the middle. Another property of the normal curve is that our first standard deviation always occurs at the inflection points of our normal curve. Now, if you're someone who has taken calculus already, then you know what an inflection point is. But for those of you who haven't taken calculus, I'm going to give you a quick little lesson. An inflection point is where our curvature or concavity changes. Curves can be classified as either concave up, I say up like a cup, or concave down, I say down like a frown. Up like a cup, down like a frown. An inflection point, or a place where the curvature changes, is where the curve changes either from frowny to cuppy or from cuppy to frowny. So I can see that this normal curve is definitely frowny here and definitely starts to be cuppy over here and over here. It's only half of the cup, but we could see if it continued, the curve, if the curvature continued that way, it would curve back up. And so the inflection point happens somewhere in here. You kind of try and look for like the flat section. To my eye, it looks like it occurs right about there. Okay, so the standard deviation then is the distance between the mean, the peak, and where that inflection point occurs. So the standard deviation is that distance right there, which is about 2.5. So for this curve, the mean is 10, it's in the center, and the standard deviation is the distance between the mean and that inflection point, so it's 2 point something. I'm going to call it 2.5. You need to be able to visually identify means and standard deviations just by eyeballing a density curve like this. Now that we've talked about the mean and standard deviation of a normal curve, I have another really important property to share with you. In a normal distribution with a mean, mu, and standard deviation, sigma, I can tell what percent of observations fall within a certain number of standard deviations of the mean. So let me draw a picture for you. Here is a normal curve. Here is the mean. It looks like my concavity changes right about here, so I'm going to draw in a line there and there. And then I'm going to kind of repeat that distance. So there's another, and there's another. Here's another on this side, and here's another on this side. All right, the first part of this rule, by the way, this rule is called the 68, 95, 99.7 rule. It's not a very cleverly named rule, but what it tells us is that if I go plus or minus 1 standard deviation from the mean, so in other words, from here all the way out to here, 1 standard deviation below, 1 standard deviation above, I capture 68% of observations. So this is mu plus 1 standard deviation. This is mu minus 1 standard deviation. I capture 68%. If I go out 2 standard deviations from the mean plus 1, 2, mean minus 1, 2, I capture 95% of observations. So if I go out to here and out to here, and I do all of this, so from mu plus 2 sigma down to mu minus 2 sigma, I capture 95% of observations. And if I go out 3 standard deviations in both directions, let's try red. If I go all the way up to here and all the way down to here, mu plus 3 standard deviations, mu minus 3 standard deviations, and I get all of this. It's not 100%, it's 99.7%. Okay, and so you're wondering now, how many standard deviations do I have to go out to capture 100% of this curve? And there is not an answer to that question. This curve continues forever in both directions. It's a horizontal asymptote. Hopefully you remember what that means. It never actually is going to touch the x-axis. It's just going to get closer and closer and closer without ever touching. So you can't ever actually capture 100%. Now that's a little counterintuitive, because if we're talking about a population of people and their heights, let's say their heights are normally distributed, yes, there is a number I can go out to in either direction and I capture everybody. However, this is a theoretical model, okay? And in this theoretical model, the x-axis is a horizontal asymptote and I never ever actually capture everybody. These properties, this 68, 95, 99.7 rule, can be used to answer a lot of questions. And so I want to show you some examples of that. First of all, the amount of Pepsi that a fountain machine dispenses for a medium varies normally with a mean of 19.8 ounces and a standard deviation of 1.2 ounces. And I have 3 questions. What percent of medium cups will have between 18.6 and 21 ounces? What percent will have between 19.8 and 21 ounces? And what percent will have between 17.4 and 19.8 ounces? All right, in order to do this, I actually need a little more space. So I'm going to open up a separate file and make this a little bit bigger. Okay, so the first thing you should do with a question like this is I need you to draw your normal curve. I need you to draw in the mean. And I need you to draw in 1, 2, 3 standard deviations above and below the mean. And I need you to label them. So if the mean is 19.8 and the standard deviation is 1.2, then if I go up 1 standard deviation, then I am at 21 ounces. That's just 19.8 plus 1.2. If I add another 1.2, I'm at 22.2. And if I add another 1.2, then I'm at 23.4. Going to the left, if I subtract 1 standard deviation, I'm at 18.6. If I subtract another, I'm at 17.4. And if I subtract another, I'm at 16.2. But Ms. Kramer, do we have to do this every single time? Yes. But Ms. Kramer, that looks like a lot of work. I don't want to do that every time. Too bad. This is what they need to see on the AP exam. Okay, in order to show your work and justify your answer, this is what you need. So for the first question, between 18.6 and 21 ounces. Since I've done what Ms. Kramer told me and drawn my picture, I can easily see that from 18.6 to 21 is going out 1 standard deviation in both directions. So I know that my rule is called the 68, 95, 99.7 rule. By the way, this is also called the empirical rule. And so I know that the answer to my first question is 68% or 0.68. Second question says, what percent will have between 19.8 and 21 ounces? Well, 19.8 to 21 is just half of what I was asked to find in the previous question. And since I'm looking symmetrically over the mean, okay, I know that this piece right here and this piece right here are going to have equal areas. So what I'm going to do for this one is just take my answer to the previous one and cut it in half, basically. So 34%. Last question, what percent will have between 17.4 and 19.8 ounces? 17.4 to 19.8, and we're stopping there, so I'm going to erase this. 17.4 to 19.8. Now, common misconception, you might see, okay, I went 2 standard deviations. This spans, 2 standard deviations, so it's 95 or it's 68 or something like that. Or you may think, okay, this is 34, so this must be 34, and my answer is 68. 68 is not the answer because these 2 pieces are not equivalent. They're not the same area as each other. What I need to look at this as is going out 2 standard deviations, but then only doing it on one side of the mean. Does that make sense? So I'm going to take 95%, which is what the answer would have been if I had gone from 17.4 all the way up to 22.2, and I'm going to cut that in half. Okay, and so my answer is going to be 47.5%. Let's take a look at another example, and this time I want you to do this. The weights of healthy newborn babies are normally distributed with a mean of 7.2 pounds and a standard deviation of 1.1 pounds. And then I want to know what percent of babies will weigh more than 8.3 pounds, between 5 and 8.3 pounds, and less than 3.9 pounds. These questions are harder than the ones I just did with you. So let's pause the video for 10 minutes and allow students to work through these. Please help each other. Please ask each other questions. And then when you unpause the video, I'll go over this. Please, please, please tell me that you started by drawing a picture. You shouldn't have forgotten that already. And so I'm going to draw my normal curve. I'm going to draw in the mean, 7.2. I'm going to go 1, 2, 3 above, 1, 2, 3 below. I'm going to add 1.1, so that's 8.3, 9.4, 10.5. I'm going to subtract 1.1, so that's 6.1, 5.0, and 3.9. My first question says, what percent of babies will weigh more than 8.3 pounds? Now, guys, there are probably 20 different ways of looking at this. I'm just going to show you one. If you did it a different way but came up with the exact same answer, then I'm okay with it. If yours is close, I'm not okay with it because with this, we should really be getting the exact same answer. Okay, 68, 95, 99.7. More than 8.3 means I'm starting at 8.3, and where am I stopping? Nowhere. Okay, I'm going up forever and ever and ever to infinity. Okay, so here's the thing, guys. Because it continues off for forever, I can't really reasonably think of this as adding pieces together because there are infinitely many pieces here. I'm actually going to think of this as a subtraction problem. I'm going to think of this part of the curve, which, guys, this is literally half of it. Half of it's over here and half of it's over here. So I'm going to call that 0.5 or 50%. Actually, let's call that 50%. And I'm going to subtract just this part, which is going to leave me everything that I shaded in over here. Now, in the previous problem, we found that 1/2 of going out 1 standard deviation is half of 68. So this should be 34%. So 50% minus 34% leaves me with 16%. Second question, what percent of babies will weigh between 5 pounds and 8.3 pounds? So let's use a different color. From 5 to 8.3. So I want everything in orange. For this, I think for me it makes the most sense to think of this as an addition problem. I'm going to add together this section over here and this section over here. Now I know that the part I just did in turquoise is 34%. We've mentioned that several times. So I'm going to take that 34% and I'm going to add this purple part. Now this purple part is going out 2 standard deviations, but only in one direction. So that's going to be half of 95%. So that's 34 plus 47.5, which gives me 81.5%. Okay. Last question. What percent will weigh less than 3.9 pounds? So here's 3.9. Less than 3.9 is everything to the left of it. Where do I stop? Never, never, ever, ever. All right, so again, I think we need to think of this as a subtraction problem. Let's see if I can erase this stuff. I'm going to I'm going to basically take this half of the curve, so 50%. And I'm going to subtract everything from 3.9 to 7.2. Now from 3.9 to 7.2, that's 1, 2, 3 standard deviations, but only in one direction. So I'm going to do the 3 standard deviations, 99.7, and I'm going to cut it in half, which is going to give me everything from 3.9 to 7.2. Okay, so that's 50% minus 99.7 divided by 2 is 49.85, which if I subtract from 50 gives me 0.15%. Not 15%, 0.15% or 0.0015. Oh gosh. .0015. If you don't like these, okay, if this doesn't make sense to you, first of all, go practice. I just taught it to you. But second, we're going to learn some stuff on Monday that's going to not replace this, but make it a little bit easier, okay? So if you don't like this, bear through it right now, but this is not a huge skill that you'll do on every single AP question ever. This is actually not a huge thing because there's a much more universal way of solving these problems. You notice I keep having to use the numbers that put me exactly 1, 2, 3 standard deviations above or below the mean. We can actually answer questions using any number using a technique that I'm going to teach you on Monday. Okay, so if you don't like this, try, practice, hold tight, it's going to get easier. And that's it for your first lesson of Chapter 2. Here's your first homework. Hopefully you have learned that doing the homework as it's assigned really is more effective. I also want to warn you that we're going to move through this chapter really quickly. All right, there's not a whole lot to Chapter 2. And so our first quiz is actually on Tuesday. We're going to learn some more stuff on Monday, and then you have your first quiz on Tuesday. Also, since we are in Chapter 2, these problems are now Chapter 2 problems. So 5, I only want you to do parts A through D, is going to be problem 2.5, 2.7, 2.8, 2.12, 2.13, 2.25. Okay, and again, next quiz is on Tuesday. It covers what I did in this video as well as what you're going to learn on Monday.